thank you for coming. Thank you for coming, especially after lunch. I hope to keep this quick-paced, and if you have any questions to spice it up a little bit further, then please feel free. We're all quite heavy. So, my name is Sasha. I work at a company called Sell Group. It's a training and consulting company based in Israel. So I fly all the way here a couple of times a year for various DevWeek conferences. And our topic today is task and data parallelism. So what I sort of assume is that you have played with or even actively used the TPL APIs, the Task Parallel Library of .NET 4. If you haven't, I will have a couple of slides just sort of recapping the major features, but I do encourage you to look at them more closely later on. There's a bunch of reference material online, talks maybe at this conference even, of course books and other resources. My focus is going to be more about applying the TPL, so I'm going to show you a few examples of typical situations in which I find there are some pitfalls that you could avoid. We're going to look at them with a very powerful measurement tool, which is the Visual Studio Concurrency Profiler. And there's going to be a bunch of tips, tricks, and various best practices. My contact details are in the last slide, and I will post all the materials I use. The slides are already up on the website and in the DevWeek app. And the code I'm going to use, I will post to my blog. Finally, and I forgot to say this in the morning, there is a link to a survey at the inside the DevWeek app. When you enter a session, there's this option of checking in, rating the session, and providing additional feedback. So please go ahead and use this option if you have the DevWeek app installed, and you can do this after the fact, so you can go ahead and fill in the evals for all the sessions you've been at so far. I think speakers and the organizers will value this feedback from you. So why are we here? Why are we still here talking about the fundamentals of concurrency, best practices with concurrent and parallel applications in 2014 if we had multi-core CPUs on commodity hardware for over 10 years now? So what I find from my consulting work, from meeting developers, from working on projects myself, is that we sort of still don't know how to adapt concurrent programming and parallelism in our applications. Many of us are lucky enough to work inside a framework that manages this for us, like ASP.NET, which will create a bunch of threads for you and call your code on these threads. And so maybe, just maybe, if we're inside the confines of a very closed framework like ASP.NET, we might never think about creating additional threads or synchronizing work between worker threads because each request is being handled completely autonomously. But again, some of us are not in this situation, and we do have to apply concurrency and parallelism to our code to get the benefits of the hardware. And we're getting more and more cores, obviously. They are getting more powerful. Synchronization is getting more and more expensive. And there's still a body of best practices, tips, frameworks that's being developed. And it's a very active area, really, for Microsoft and for other players in this area. And so this is sort of why we will still probably need talks like this in 10 years as well. So in terms of the TPL, which we're going to be based on in this talk, the Task Parallel Library was incubated for some 3 or 4 years as the parallel extensions for .NET. And I actually went up just a few minutes ago and found a blog post that I wrote on December 1st, 2007, titled The .NET Parallel Extensions December CTP. And this was the first public preview of the Task Parallel Library in a very, very limited shape. And one of the foundational statements that Herb Sutter has been quoted to say is that concurrency is the next major revolution in how we write software. And I'm not sure, again, that this has quite happened already. This is a revolution that's been happening very slow, or maybe is to happen a few years from now. So we still need the tools like the TPL to help us with this revolution. It was released finally in 2010 with .NET 4 and has been improved since a little bit in .NET 4.5, specifically in 2 directions. One is TPL data flow, and I've just been to an excellent talk right before lunch about TPL data flow, which I strongly recommend you to watch online after the conference. I believe everything's being recorded here. And it explains how the TPL data flow library framework can help you expand your parallel applications if they're structured in a certain way, if order is important to you. I will also mention the TPL data flow library later on. The other direction that the TPL has been going in is language-based concurrency, language support for asynchronous operations, which we all use in C# 5.0. These are the async and await keywords. But this is only for asynchronous operations. It doesn't help you parallelize anything, it just helps you do operations concurrently. So in terms of future trends, what I would like to see from the TPL or from other libraries provided by Microsoft are a couple of things. The first is GPU concurrency. Graphical cards that you have in your laptops and desktops today have many, many more cores than your chips, than your CPUs that you have in the same computers today. And we can't quite tap into that concurrency with .NET code just yet. So this is a direction I'll be very happy to see us go in, because lots of computing-intensive tasks can be parallelized wonderfully on the GPU, on the graphical cards, which mostly sit idle unless you're playing high-intensity graphics games. The other thing is SIMD support. SIMD is single instruction multiple data, which is a feature many processors have for about 10 years now as well, which allows you to perform multiple operations in a single instruction with the latency and throughput of a single instruction, like multiplying numbers, like getting the square root of a bunch of floats. So there are operations that can be parallelized by using CPU instructions. And this is again something that we cannot do today in .NET code. In C#, we don't have access to assembly language, and we don't have libraries which expose this underlying support quite yet. And the third area is language level parallelism. And this is something, again, that many languages don't have today, but there are proposed extensions, for example, to C++. Intel have a set of proposed extensions for C++ that allow you to express parallelism at the language level, saying, here's a loop, I want this loop to run in parallel using a language keyword and not a library. So these are three directions which I believe the TPL will be facing, or at least addressing in the future releases. This is not based on any internal knowledge, this is sort of wishful thinking, informed wishful thinking. So let's start with reviewing some of the APIs that shape the task parallel library today, the core of the task parallel library. I'm leaving the data flow code, the data flow framework behind for now. So a task in the TPL taxonomy is a unit of work which specifies a piece of code that wants to be run somewhere at some point. A task does not have the execution resources associated to it until you put it on a queue, which is then, scheduler, as you like to say here, I find it really difficult. So until a scheduler grabs it off a queue, and that scheduler then assigns it to a particular thread of execution. So a task is this abstract piece of code, piece of work that has maybe some inputs and some outputs, might end in an exceptional condition, might be canceled, but it doesn't know where exactly and on which thread of execution it's going to run. And this is an abstraction that helps because tasks are much cheaper than threads. And we will see an example very soon where creating very many tasks is going to be expensive as well. But very many tasks is like millions of tasks. That's what I call very many tasks. If you create 2 million threads, a few million threads, for example, you're gonna crash completely, even on very high-end systems. So there is quite, yes, hello.
Just stop you a second.
I didn't unmute it, did I?
No, that's the one.
Of course I didn't.
There you go.
Okay, so you could hear me before though, couldn't you?
Yeah, but we need it for the recording as well.
Gosh.
Okay.
Okay. So if you're watching this later, you have just missed 5 minutes of introduction, which weren't really quite as important. So now we're actually getting into the APIs. So yeah, a task is a piece of code that doesn't know where exactly it's going to run, and you can create many tasks as opposed to threads. So you don't have to worry about exploiting the hardware about using just exactly the right number of threads for the computing resources that you have. So here's a couple of examples if you haven't seen the raw task support in the TPL before. I can create a task that returns a string and pass in a function, a lambda in this case, which just goes ahead and does something, which eventually returns a string. I can associate this task with a set of continuations. For example, if the task ends up faulted, which means there was an exception that happened during that task's execution, then I can issue this continuation, which is again a lambda function, which takes in the task and displays the exception that occurred. And if the task ran to completion, then I can associate it with another continuation, which is again some other lambda function, which takes the task and displays the result. And while the task is running, I of course can do completely different things. And I can query the task for progress, I can wait for its completion, and in C#5, I have the language support to do this asynchronously with the continuations as before, but without writing so much library code. So I could create a new task that runs a certain function. I can await it to get its result asynchronously by associating a continuation that runs once the task ends successfully. And to handle exceptions, instead of associating it with another continuation, with the only unfaulted condition, I can simply use a try-catch block. And the compiler does the heavy lifting. The compiler will wrap this thing up with a bunch of continuations and schedule each continuation exactly when necessary. So this is what we get from tasks. It's a way of taking a bunch of work items and scheduling them off to someone else, to the scheduler, which might execute them all on the same thread or in a bunch of threads, and the entity that decides how many threads exactly are right for you is basically the .NET thread pool, by default at least, when you schedule your work to the default thread scheduler. Now, these APIs are quite useful, and we're going to explore them in a demo very soon, but they work well when you really know exactly the shape of your work items, and when you can generate a lot of work items, like maybe hundreds, thousands, tens of thousands work items, because that's when you can really benefit from concurrently executing them. If you can only produce 3 work items when asked, then you can at most use 3 threads and 3 CPUs. So if you can somehow, maybe using recursion, maybe by splitting your work into chunks and pieces, if you can produce a lot of little work items, then you can benefit from creating a bunch of tasks like that and just handing them off to the scheduler. In other cases, it might be easier to parallelize your work, to split it into pieces by using the parallel loop support, which we also have in the TPL. So this is still just basic API coverage. We have a couple of functions, parallel for and parallel for each, which are designed to parallelize a loop. So basically, in the case of parallel for, you've got a for loop. You have to perform a certain operation over a large number of iterations. You specify the ranges, the begin and end of your iteration range, and a function, a lambda, for example, that will be called for each number in that range. And again, the number of threads that are going to use, that the TPL is going to use for running this loop is going to be determined by a combination of the scheduler and the thread pool. In this case, the number of tasks is also not up to you. You don't specify, well, I want 300 tasks. You just say, here's a range of iterations, and someone goes ahead and splits that range for you. And again, we're going to explore this splitting shortly. So parallel for and parallel for each are easy ways of taking a loop that does not have any iteration interdependencies and parallelizing it just like that. If you do have dependencies, for example, iteration number 7 cannot run before iteration number 4 has completed. If you have complex dependencies like that, then parallel loops are probably not going to work for you. You're going to end up blocking for results, or you might end up producing wrong outputs. So in these cases, we'll need more complex dependency management, and that's again coming up a bit later. And finally, one API that I personally haven't been using very actively is what's called parallel link. So basically, you can take a query that you designed using the C# support for link queries, a query that maybe selects some data, filters some data, orders some data, perform some compute-intensive work on a bunch of items in an enumerable collection, and then produces some output. You can take a query like that and just tack on an as parallel at the end. If you have, again, the TPL namespace imported. This is an extension method on any enumerable that turns it into a parallel enumerable, which will then execute the rest of the query in parallel. So in this case, for example, the evaluation of monster is attacking, and the evaluation of the simulate movement function, and finally even the order by itself is going to be partially executed in parallel. So there's going to be a set of threads here executing these operations concurrently, and then the output of this query, which you actually ask to be ordered, is going to flow through to the next component that wants to process it. And if you use the for all method, which you can only use with parallel enumerables, then the rest of the query, the actual evaluation of whatever I write here, will also happen in parallel. So the concurrency just flows through. Parallel link is really nice, and I mean, it can't be easier to parallelize anything than just by tacking as parallel at the end of your enumerable, but it does mean that you have to express your whole computation as a link query. And I mean, you can't always do that. But if you can, this is a really easy way of parallelizing link queries. So we have these three APIs: tasks, parallel loops, and parallel link. Let's take a look at them in more detail. We're going to use the Microsoft Visual Studio Concurrency Visualizer for that. It used to be a tool that was part of Visual Studio. You'd get it with the Visual Studio installation since Visual Studio 2010. In Visual Studio 2013, Microsoft have, for some reason, decided to split it into a separate Visual Studio extension. So when you install 2013, you're not going to find the Concurrency Visualizer. You have to install it separately from the Visual Studio extension gallery. It's not free. I mean, it is free if you have Visual Studio Ultimate, which is sort of a funny way of saying you get it for free if you're paying $13,000 for Visual Studio. I think it might be also part of the premium edition. There are alternatives. There's Parallel Studio, which is an Intel tool, and you can get some of this beautiful visualizations that I'm going to show you for free if you use the Windows Performance Toolkit. But it's going to take lots and lots more work to just juggle the data together and get exactly the same visualizations that we'll see. So this is a powerful tool, but it is still pretty expensive. And what it lets me do, actually, is, well, as it promises, to visualize the concurrency of my application, to understand what threads I have and what they're doing at any given time, to see where I have tasks and parallel loops, to see where my threads are blocking and where they're executing code, when they're issuing I/O requests, which requests these are. So basically, this is a tool for flowing through your application's execution on multiple threads and seeing exactly what happened at every point in time and also what happened on a more higher level view. So we're going to see this tool in a couple of scenarios soon. So let's start with applying tasks. We're using tasks at this lowest level of abstraction, no loops, no data parallelism, just, we are responsible for breaking a piece of work into smaller chunks and parallelizing that. So the example I'm going to use here is different from what I'm showing you in the demo. And this here is the known Fourier transform, the fast Fourier transform calculation, which is basically a recursive function. And this is all we really need to know. So essentially, we have a couple of arrays, float arrays, and a couple of numbers here, which are basically a range of values that we're operating on. And the FFT function here simply checks for the base case when we only have one element to process. If we have more than one element to process, then we split the computation to a couple of different recursive calls, each for 1/2 of the original array. And finally, there's a step omitted here which combines the two halves, and this takes linear time. So basically, this is a recursive divide and conquer style of algorithm where we have this recursive call for two different halves of the input array, and each is processed autonomously. There is no dependency between the left and right-hand sides. So, well, parallelizing this is just a matter of parallelizing these recursive calls. Someone has already taken care of, by designing this algorithm, of splitting the work into smaller chunks, into recursive smaller chunks. So all we need to do is basically slap a task or a parallel invoke on top of this thing. And this might work, and again, we'll see that it doesn't really hold in all situations, but the general idea is definitely to use this built-in concurrency opportunity and run the two branches in parallel. Parallel invoke, by the way, if you haven't used it before, will just create two tasks for you and then wait for both tasks to complete. That's all it does, really. So you could use that, or you could create two tasks and then use task wait all, whatever API you prefer. Now, the problem with this is that the leaves of this computation are really rather small. Towards the end, we get to the base case, which is basically like 3 CPU instructions. This is what it takes to evaluate if n is equal to 1, then do this, and then return. So we keep splitting and splitting and splitting, and producing more and more little tasks until we produce tasks that only execute like 3 CPU instructions. And I mean, tasks are good and cheap, but if you end up creating tasks that execute 3 CPU instructions, you're going to introduce a lot of overhead. Creating a task involves a heap allocation, which already requires locking and puts pressure on the garbage collector. Obviously, this task object that's allocated also has to be initialized with a bunch of different fields. When the task completes, there's another bunch of post-completion work that has to happen. So you really have to limit your recursive structure of the splitting of work to little tasks to a certain threshold. So let's take a look at an example of this with a different, fairly known algorithm. Specifically, I'm going to look at quicksort. So the general idea here is rather similar in that we have this serial version of quicksort. Can you see the fonts in the back?
Yeah.
Or should I make them bigger?
No, that's fine.
That's fine? Okay, so we have this serial version of quicksort, which for simplicity I designed to only accept integer arrays and sort them. So serial quicksort takes an integer array, left and right bounds, which start with the whole range of the array. And then quicksort, if you recall, runs a function called partition, which basically picks some point in the array and arranges some of the elements to the left and to the right of that midpoint. And then we have two recursive invocations of serial quicksort. We have serial quicksort of the left and serial quicksort of the right remaining parts. And of course, there's a base case or a couple of base cases here. We don't keep recursing if we only have one element left to sort, because sorting one element is rather easy. So this is the recursive structure of the algorithm, and it's very similar to FFT, so we're going to try and parallelize it in a very similar way. So here's parallel quicksort, no threshold. Pretty much the same thing as before, except after partitioning the array and doing all of that, we create two tasks, if necessary. The left task and the right task. Let me scroll this thing down a bit. We create a left task and a right task. The left is going to do the left's part, the right is going to do the right part. And if we actually have some tasks running, then we wait for them to complete. And then we go in. So again, this is the basic recursive structure, except now we're doing things in parallel. Now I have a test benchmark over here, which will run this parallel quicksort and measure its performance. I'm doing all the measurements in release mode, repeating for several times. So from our demo menu, I'm going to pick the start. Okay, so the serial single-threaded version of quicksort completed in 174 milliseconds on average, whereas the parallel version completed in 311 milliseconds on average. And this is not quite what we wanted. Now if you look at the CPU utilization, you'll see great results. And I'm going to show you these results from the concurrency visualizer. So we have successfully used the available hardware resources. The problem is that we didn't actually make the algorithm faster. We just used more hardware resources. So if we look at the concurrency visualizer results, which I have open right here. By the way, before I show you this, the reason I'm not running it in front of you is that it takes quite a few seconds to analyze the results. But essentially what I've done is just picked concurrency visualizer from the Analyze menu in Visual Studio, and then said, start with current project. And it launches the current project and analyzes its concurrency work in the background. It relies on event tracing for Windows, which is a really powerful framework that can collect events for context switches, creating new tasks, blocking on I/O, blocking on synchronization object. So this is all based on support that's already part of Windows. So I've done this and got this beautiful report, which looks like this. What I see here is my application's CPU utilization. So this is a graph that shows me the number of logical cores that I've actually been using throughout the computation. And it starts with this section over here where I'm only using one logical core. This is the serial single-threaded version of the algorithm. And then right over here, this chunk over here is the part that we have parallelized. And I'm still not quite able to reach 100% CPU utilization, but it's much better than previously, again, in terms of just looking at CPU utilization, where we're using our hardware resources more effectively. But there's a bunch of spikes here, and again, the result is that we have a slower program, so it's worth digging in a little more detail. If I dig in, I can do this using the Threads tab, which shows me several things. First of all, there's a bunch of markers like this. For example, you can see this marker over here that says task 2 executed, task 2 completed. And then I have a marker over here that says beginning wait on task 1. And I have this span over here, parallel quicksort no threshold. Some of these markers I generated, like this one over here is something I wrote code to generate. The rest of these markers are from the TPL. The TPL produces a wealth of information when you create a task, when you schedule a task, when a task completes, when a task fails, when a task waits for another task to complete. There's a bunch of info out there. And one thing you can see is that during the course of this computation, we had this really big task over here, task number 2. And this looks like, you know, a big mess. But anyway, it looks like more than one task. So basically what we had is one task that somehow resulted in just running for a very long time and a bunch of messy work items over here. If I scroll down, I can see a bunch of more information. Task 1 executing, task 1 completed, beginning synchronous wait. All of my tasks eventually will show up here. Towards the bottom, if I scroll down enough, I will also see threads. These things over here are various threads I have in my application. And the colors are what the threads are doing at any given time. Green is execution. This is a thread that's running on a certain processor. This pinkish whatever is a thread that's waiting. This is synchronization. And you'll notice that if I look at the visible timeline profile report down here, then you can see that I'm only using 20% of my thread's total time for execution. So I have many, many threads. 80% of the time, overall the threads, I'm just sleeping, waiting for something, waiting for a synchronization mechanism, and 20% of the overall thread time, I'm actually executing. It doesn't mean that I'm only using 20% of my CPU, but it does mean that I have a bunch of threads, and many of these threads aren't actually doing anything useful, like waiting for some task to complete. Now, I can inspect these threads in more detail. I will do this later, but for now, I just want to show you something that will be pretty incredible. If I zoom in on this region, over one of these markers over here, which these markers belong to the following category: beginning wait on task something. Or maybe we can look at these markers over here, which belong to the category a task has started executing. So if we look here, the tooltip says there are 4,061 flags in this region. And then I move to another region, there are 3,051 flags in this region. And then I move over, there are 5,173 flags in this region. So from this, I can already tell you that we have many, many tasks going on. And if I zoom in now, and zoom in again, and zoom in again, and zoom in again, and zoom in again, eventually, after a lot of zooming, I will reach the individual task scheduling events. So I can keep doing this. Here we go. So this thing over here says task 933,778 was scheduled to some task scheduler. So we have like millions of tasks created during this computation. So it is not quite surprising that we have this huge overhead in terms of CPU time. And right now, by the way, the zoom level we're at, just take a look at the zoom level. This is in microseconds. So this region we're looking at here is maybe like 80 microseconds or so. So you can see these individual events if you're really interested in them. But in our case, the problem is that we have too many of these individual events to look at. We have millions of tasks, and that's the exact thing that we're trying to get rid of. So the general principle with this sort of problem is to simply decide that we want to limit the number of tasks that we create. There are several approaches to this. We could limit the depth of the recursion. We could limit the total number of tasks that we have running at every given time. So we could keep a counter of exactly how many tasks we have that haven't completed yet. Or we could even use, instead of a depth-based approach, we could just keep track of the total number of splits that we perform, for example. And so what I decided to do in this third version of parallel quicksort is to pick a threshold of just over 1,000 elements, and to decide that if the remaining part of the array is smaller than that threshold, then I'm just going to fall back to the serial version and not parallelize this anymore. Now, the exact threshold, of course, is something that you have to establish by measurement. And this is one of these places where the abstraction begins to fall down, because, I mean, hypothetically, I would like this thing to be parallelized down to the very smallest tasks, but I can't afford that. So I have to pick this arbitrary number and limit my parallelization there. And it really does depend on exactly what work I'm doing. So in some situations, it might make sense to pick a depth-based threshold. In other cases, there's just this magic number. If we compare our previous approach to this, and this just means I uncomment this line over here, then we'll probably get a much better result. So now we're down to 64 milliseconds. Considering that I have an Intel i7 processor, which has 4 physical cores and 8 logical cores, we're not quite seeing a 4-fold increase in speed over here. So we had 178 milliseconds, and now we're down to 64 milliseconds. That's more like a 3-fold increase, but it's still fairly reasonable for quicksort specifically. We're still generating some overhead by this parallelization, but much less overhead than previously. And in fact, if you really want to use parallelism to sort numbers, you should not be using quicksort. Quicksort is not designed for parallelization. There are better options. You can look them up on Wikipedia, which are pretty simple to implement as well, and they do not rely on the same principle that quicksort uses. But anyway, this is a pretty nice result considering the amount of effort we had to spend here. Just took the recursion, limited the depth of the parallelization, and threw a task at each side of the recursion. So these are some things we can do with tasks, with task parallelism, where we have to split work into smaller parts. When we do symmetric data processing, on the other hand, when you have a bunch of items that we want to perform as the same operation for each item, and there are no dependencies whatsoever between the items, then again, we don't have to work with tasks directly. We can use the parallel loops here. And I'm going to show you a couple of problems with this, but first, the non-problem case. Suppose I have an image, which consists of a bunch of pixels, and I want to blur the image to a different image. Blurring basically consists of taking every pixel and averaging it with the pixels around it. Now, in this particular case, I can use parallel 4 to parallelize this operation based on the image rows. So I have a parallel 4 from 0 to the number of rows I have in my image. For each row, I run another loop that takes all the elements, all the columns in that row, and sets the pixel in the destination image to the result of blurring that pixel in the source image. So that thing is not in place. I take a source image, I generate a destination image, and each iteration here is completely independent from the others. I'm not using any shared data here, which I'm also writing. I only read shared state, and then I produce additional information to the destination image. So this sort of thing is perfectly, embarrassingly parallelizable. There are no interdependencies, and it's quite obvious also that processing every row is going to take pretty much the same amount of time, right? I mean, there's no reason this one particular row is going to be much harder to blur than some other arbitrary row. So in that case, I mean, parallel for works rather well. And it doesn't really matter very much what exactly you use as the iteration space. Could be the rows, could be the columns maybe, could be some other function, maybe the number of processors that I have. But there are situations which are more complex and do not produce this perfect parallelization. And what you see here is again a report from the concurrency visualizer, which says which threads were active during my application's execution and what exactly they were doing. And so in this sort of graph, you can see that I have 8 threads exactly, and they were running almost all the time. So this is sort of perfect as it goes. I parallelize this application across multiple threads, and they're all running all the time, and they all complete after the same amount of time. Perfect concurrency. Yes, hi. Can I help? Oh, okay, thanks. Now, there are some other situations where the work is not distributed uniformly, or when you have interdependencies between the iterations. So let's start with the non-uniform work distribution case. And again, I have an example to show you later. So for example, suppose we want to go over a bunch of numbers and check which ones are prime. Now, checking whether 7 is prime or not is going to be a little easier than checking whether 10,320,647 is prime. Now, of course, there are large numbers which are, say, even, so it's easy to check that they're not prime. But for larger, non-even numbers, it might take much longer to verify whether or not they are prime. So splitting the range, splitting the iteration space into several statically sized buckets isn't quite going to work. And again, we'll have some code to look at later, but for now, this snippet here essentially says, let's take the number of CPUs that I have, split the iteration space into that number of equally sized chunks, and process each chunk in parallel, looking for all the primes that you can find. And this results in something like that in terms of CPU utilization. You have a bunch of work that starts off on several processors, several threads, and then one finishes pretty quickly, the other one finishes a little later, the third one finishes down here, the fourth one here, the fifth one here, and towards the end of the computation, you have less than half of the original threads actually running. So this is an uneven work distribution. And again, it's a pretty common problem when you're parallelizing work that seems to be identical for each element in the iteration space, but, well, it turns out not quite so identical. So there are a few solutions to this in TPL. And one is using what's called a partitioner. A partitioner in TPL takes an iteration space and divides it into not necessarily equally sized chunks. And the number of chunks it actually ends up producing and the size of each chunk depends on what work you're doing. So it will look at the work patterns of the number of CPUs that are active and busy, the number of threads it has to create to keep that many CPUs occupied, and it will tune the number of elements in each chunk, and so the number of chunks accordingly. So for the partitioner API, in one of its variants, basically accepts a start and end of the range, and a desired hint for the chunk size, and then it will go ahead and hand back tuples that have the start range and the end range for the iteration that you have to process right now. So basically, instead of working with individual iterations, your parallel loop now takes in a chunk and processes all the elements in that chunk. The partitioner will decide exactly how many chunks to create and when to hand them off to you. So this is much more flexible from the TPL's perspective than when I say, here's the number of chunks, here's the size of a chunk, process them all in parallel. So let's take a look at this. I have here a version of this primes computation, 3 versions of it. So the first one is just this one over here, count primes. No, sorry, that's not the one. Is this one over here, uneven work distribution. So this basically says, okay, take the numbers from 0 to the number of processors that I have. This is my iteration space. For each number, run a task that finds how many primes there are in the chunk that this number specifies, and then wait for all of these to complete. So at the very most, I'm going to have p threads, where p is the number of processors. And well, the result of this is really that some of the threads complete very quickly and others run all the way down. The second version here, auto work distribution, uses a slightly different approach. So here, I'm using parallel for in its plainest overload. I'm telling parallel for start here, end here. If you encounter a prime number, well, increment the total number of primes that you have seen so far. Now this is pretty good because again, I'm letting the TPL choose exactly how many chunks to create and what size each chunk should be. But there is a slightly different problem with this, which we again get an opportunity to optimize. The problem here is that each iteration could be very, very fast. For example, half the numbers in our iteration space are even, right? And determining that a number is even involves basically like 3 CPU instructions. And it's probably the first thing we're going to do if we want to find if a number is prime or not. We're going to divide it by 2 and see what happens. And so for these even numbers, which are half of the iteration space, this loop over here, the body of the loop, is going to be like 10 CPU instructions. So we end up calling an iteration of the loop for 10 CPU instructions. Now, this iteration here is eventually represented as a delegate that you have to invoke with a parameter. And this involves calling a function through a function pointer, calling a delegate through, calling a function through a delegate. And this can be more expensive than the actual body of the loop if the check that the number is even is very fast. So the opportunity for optimization here is that the loop body, which we actually provide as a delegate, can take a chunk and not just a single iteration, not just a single number. And this is again something that the partitioner API gives us. If I use the partitioner API, then the loop body I provide takes a chunk, which has a start and end. It's a tuple that has item 1 and item 2. And so I use that, a chunk, and the iteration body is going to be less expensive to call. So this basically just reduces the overhead in calling a delegate. And is this really sizable? Let's check. So this is the second demo here. The uneven version takes 387 milliseconds. The one with parallel for 292 milliseconds. And the partitioned one, where we use chunks instead of single elements, is actually a bit slower. So in this particular case, it probably doesn't make sense to use this optimization. It's good enough to just let parallel for partition the range for us and not worry too much about each individual iteration being invoked as a delegate. But in either case, it is considerably faster than the naive approach, when we just pick a number, split the range into a static number of chunks, and then work on each chunk in parallel. Unless, of course, we pick a really high number. If we use 1,000 chunks, then maybe we'll find better results. But if we use the number of processors as the number of chunks, that works out pretty badly. So the third thing I want to take a look with you at is dependency management. As I mentioned, when you use parallel for each, sort of the implicit assumption is that you don't have nasty inter-iteration dependencies. Like iteration number 7 depends on the results of iteration number 3 and stuff like that. If you do have these dependencies as part of your algorithm, just that's the way the algorithm works. It really needs this information from previous steps. then our life is much harder. And I have one real nice example of this to show you. There is an algorithm called edit distance, which basically accepts two strings and finds how similar the strings are. The edit distance is defined as the number of changes that you have to make to one of the strings to get to the second string. And the changes that are allowed are inserts, deletes, and replacements of a character. So if you have cat and hat, you can replace the C with an H and you get the other word, so the edit distance is 1. If you have at and cat, then you have to add C from at to cat, so again the edit distance is 1. Now, there is a pretty simple dynamic algorithm that finds the edit distance. And the idea basically is that you have a two-dimensional table and you find the edit distances progressively. Now, this is something that you could conceivably parallelize. You have a two-dimensional table, and the basic idea is that you fill in the cells in that table, so you can fill the cells concurrently. Each cell can be filled on a different task, for example. The only problem is that each cell depends on a bunch of previous cells. For example, the orange cell over here depends on the cell immediately above it and immediately to its left. And say this cell, lighter yellow cell over here, depends on the cell on top of it. So we can't really just say parallel.for, take all the cells in that table, and just run and parallelize all this work. We're going to end up with incorrect results. We need to impose order. And there's a bunch of imposing to do here, because again, there's a huge number of dependencies. So the idea here is to proceed in a wavefront. We start with a single task that calculates this value over here, which is really necessary for any further computation. And then we can find the values of this cell over here and this cell over there. And then we can find this one, and this one, and this one, and so on and so forth. So we build up this wavefront, which eventually takes over the whole table, and we get the result in the bottom right corner, which is the final edit distance. Now this is pretty hard to code, so I've just stolen the sample from someone else. This sample is part of the samples for the task parallel library, which was released on code.msdn.microsoft.com. And this particular one was written by Stephen Taub, who was an architect on the TPL team. Well, he was an architect on the TPL team. He really knows what he's doing. And he has this class parallel algorithms with a bunch of wavefront functions. Now, we won't have time today to explore all of this code, but it's basically what I've told you. It takes a set of definitions over a two-dimensional table, which defines exactly what dependencies you have, and executes tasks in a wavefront until it's covered the whole thing. And it uses continuations extensively, because the premise is that you take a bunch of tasks like this one, and then you schedule a continuation that says, when this one and this one complete, then start off this one, and also this one and also this one. So you have continuations from a set of tasks to a set of tasks, and you have to manage these continuations quite carefully. Now, it might sound like there's not enough work to parallelize here, but for longer strings, for example, DNA sequences and not words in English, finding the edit distance can be a pretty laborious process. And of course, I mean, not of course, but I think geneticists are not actually using the edit distance algorithm for that. But if they are, this is a good opportunity for parallelization by using this sort of waveform. So again, I have a demo of this already implemented, which basically goes like that. So I'm building random strings, pretty big ones, 4K strings. And the parallel version is over here, and its core is just calling this parallel algorithms.wavefront function, which does all the heavy lifting with the continuations. And all I had to do is just sort of use it. Again, I'm not going to go over all this thing over here, but let's just run the benchmark. So this is the third version. And this is pretty neat. I mean, the serial version takes 195 milliseconds on average, the parallel 164 milliseconds. Again, it's not a four-fold decrease in time, but it's not bad at all, again, given that this is a really hard problem that has a lot of dependency information. I really can't just parallelize this whole matrix naively. I have to take care of all this continuation information. And so, considering that overhead, the fact that we get a more than threefold speedup is pretty impressive. So that's another example of applying this idea of tasks and dependency management to a real situation. The fourth thing I want to show you before we move on to some more exotic tricks is the concept of aggregation. One of the biggest problems in parallel algorithms is that you have too much synchronization baked into the algorithm. For example, when finding prime numbers, I was keeping track of this shared variable that says how many prime numbers I have found so far. This is like a very simple example, but this shared variable of how many primes I've found so far is a variable that I have to update atomically in a synchronized fashion every time I find a new prime number, and there are quite a few of them. So on the one hand, I mean, I would like to just not use any shared state at all, work in a completely functional sort of approach. But I mean, real life situations just don't work that way. You have some shared state that you have to rely on, that you have to update. And one approach for reducing synchronization is through the concept of aggregation, where instead of accessing shared state, you have local state for each thread, or for each task, or for each chunk of the iteration space. And you can update that local state freely without using any locks. But at the end of your computation, you have to combine all of these local states into a single, consistent shared state. Now, it might take more memory, it might end up using more CPU cycles, but supposedly, because you have less synchronization, you don't have threads blocked on global state. Each thread is working with its local state, and then at the end, you have to combine all these local states into one shared global state to merge. So here's the basic form of the APIs that we have for parallelization using aggregation. Parallel for each and parallel for are equipped with overloads that help with aggregation. So take a look at this one over here, parallel for each. It takes an enumerable, which is here created using partitioner.create, could be just a plain collection. And then it takes 1, 2, 3 delegates. 3 lambdas in my case. The first delegate initializes the local state for each thread. And in our case, the local state is a list of ints, list of integers. The second delegate is the actual work to be done. This is the function that takes in a chunk, finds the prime numbers, and updates the local state. So it takes 3 parameters. The first is the iteration variable. The second is parallel loop state, which we're not using here. Parallel loop state is a class that you can use to break out of the loop, to wait for other iterations, various coordination tasks like that. And the third variable, the third parameter really, is the local state. So I have the current iteration, and I have the local state, and my work now is to take that current chunk, find the prime numbers, add them to this local state without using any synchronization, because this is my private local list. No other thread has access to that list. And then finally, I have to return a new version of that local state. In our case, it's a reference type. It's a list. So I return the same instance I was provided. I just added a few elements to it. But you can use aggregation with maybe integers. And then you get in your previous local state, you return some new int, which is the new local state. But this whole thing does not require synchronization at all. This local list is only accessed by my thread. The problem is that at the end of this computation, I have like 50 lists of prime numbers, and I have to combine them to a single big list of prime numbers. So this is the task of this third delegate over here, which is passed the local state for each of the threads and combines them in whatever way you need. So this lambda will be invoked for each of the local states that your algorithm was using. So this is the general shape of an aggregation-based loop. You have something that initializes local state. You have something that combines local states into a global shared state. And you have the work itself, which references and updates the local state, which is only used by your thread, so you don't have to synchronize access to it. This is a very effective way of reducing synchronization. And I want to show you an example which might be a bit surprising. So what I have here in this matrix sum class is a really simple example of traversing a matrix and finding the sum of all the elements in parallel. This is like really a trivial example, but again, it's quite surprising. So I have three versions as usual. I have the sequential version, which takes a two-dimensional array, a matrix of ints, and finds the sum of all the elements. Goes over the rows, goes over the columns, sums up all the elements, and stores the result in some shared variable. This is version number 1. And this is sort of the baseline. The second version is this. Traverse matrix parallel. What I'm doing here is the following. I have a sum local variable initialized to 0. And then I go over all the rows in parallel. Each iteration takes a row and goes over all the columns and adds the whatever we have in the matrix to this shared sum variable over here. And I have to use interlocked add for that because why not just sum plus equals matrix at ij?
Size of the variable.
Mm-hmm.
Because probably 4 bytes or 8 bytes. So it's not atomic.
It's a shared variable which I need to read and write,
Yeah.
right? I'm updating a shared variable from multiple threads, right? So I need synchronization. Parallel 4 is going to run this loop on multiple threads. I'm accessing a shared variable from all of these threads. Am I? I think I am. And so I need synchronization here. And interlock.add, which I will mention, by the way, in a couple of minutes, interlock.add is a hardware primitive that performs an atomic operation of adding a number to some memory location without requiring locks or any additional synchronization. So this is correct in terms of synchronization. I'm updating this shared location in a correct fashion. The only problem is that, of course, using this interlocked add function is more expensive than just, x plus equals matrix at ij. It's more expensive than just doing a standard add. But we need something here to protect the access to the shared variable. Now, it is a local variable of the traverse matrix parallel function, but I hope you're not confused by that. I mean, it is a shared variable that all of these threads are going to see and access at the same time. Right? So this is the second version. And the third version gets rid of just one single point of synchronization. This is the version that uses sort of pseudo-aggregation. It's not really using an overload of parallel.4 that supports aggregation. It's doing something else. I still have this shared sum outside of my parallel loop. Inside the loop, I have a local sum, which I use to find the sum of this particular row over here. And then I do interlock.add only once, outside that loop. So I do interlock.add once per row, and not once per cell in my matrix. That's the only difference with it. How bad could it be? I mean, there wasn't so much synchronization to begin with, and I've gotten rid of that very little synchronization that was there to begin with. But as you can imagine, I'm showing you this because there is quite a difference. So the serial version takes 20 milliseconds on average. The parallel version with the shared access with the interlock.add takes 370 milliseconds on average, and the one with the aggregation takes 6 milliseconds on average. So, I mean, by getting rid of that very little synchronization, we were able to improve the results quite significantly. And the problem here is that this synchronization really brought performance down 30-fold, right? Again, CPU utilization was higher. We probably were using 100% of our CPUs, but the overall running time was 30 times longer. So the problem here is that this inconspicuous operation, which requires shared access, shared read-write access to this global shared variable, is very bad for CPU caches. It turns out that when you do something like that, which requires read-write access to a variable that another CPU is also trying to update in a similar fashion, then you're both kicking this value out of each other's CPU caches. When I want to update this sum variable, I tell all other processors, get this out of your cache so I can update it. When another processor wants to update this value, it tells all the others, including me, kick that value out of your cache so I can update it. And the result is that you have a lot of ping pong like that on the bus, on the memory data bus. And of course, when you access this shared variable, you always go to main memory. You're not using the cache at all. So all of those reads and writes invalidate caches on all processors all the time. And yeah, it's pretty bad. It's so bad that we get a 30-fold slower result. And this is on a system that only has one socket. I have one CPU with 4 cores. If you run this experiment on a system that has dual CPUs with multiple cores each, you might see much worse results. Because this ping pong between caches is even worse when you have multiple CPUs and not just cores on the same CPU. So shared state is really bad. And it is bad when you just use plain locks. And it's also very bad when you use this magic atomic hardware instructions. So these were the 4 core examples that I wanted to show you. And from here on, I have a couple of miscellaneous tips and bits that I'd like to share with you as much as time permits. And please, of course, question.
The fastest example, one with the increment at the interlock add at the bottom. If you change that to be tasks instead of using the parallel form, do you see any difference at all? I mean, it would be the
Here,
same.
if I use tasks,
In the third one,
Yeah,
you're updating the sum after the loop.
over here,
Yeah, so if you, instead of it being parallel for, you made that a task which returns the local sum at the end of its completion.
that's fine.
Yeah, would that be of similar performance or would?
Yeah, that's fine. I mean, if I use a task that returns the local sum, then I have to keep that local sum as a local variable, and then I'm not accessing shared state. Yeah, so absolutely, it's also an option. Yes, sir.
So you said there's an object called a concurrent bag, so you can have a single object and it handles all the thread local copies for you.
Yeah,
Is
well,
that a possibility and this kind of thing?
concurrent bag is a collection which you can add elements to. So, for example, in this example, on the slide, when I was collecting all the prime numbers into a single shared bag, then yeah, absolutely. Concurrent bag would be a great collection choice in this situation. I don't have any slides of the concurrent collections, but concurrent bag indeed is designed for the situation where you have many, many threads inserting items into the same collection and then pulling items from it as well, but it doesn't really matter in our case. So yeah, concurrent bags have thread local buffers for whatever you put in them, and then towards the end I could write a loop that turns it into a list-defined sys. But yes, I mean, I would not have to use this sort of local aggregation, and it would probably be pretty equivalent. Because inserting to a concurrent bag, in most cases, doesn't take any locks. But, I mean, I wanted to show you aggregation explicitly. However, in our case, with the matrix sum, I mean, I'm not using any collection at all. So I needed this aggregation explicitly. Right, so the first tidbit I'd like to share with you is this problem here, which is an actual, totally real-world problem that I had to solve at some point and come up with some options. So suppose we implement a collection of stock prices. We have this really powerful system that receives updates from the stock exchange, a bunch of updates every second of various kinds, which I'll explain in a second, and we have to keep the very last ticker of a particular stock at every given time, and we have 100,000 different name price pairs for stock information that we maintain. Now, the operations that we get are reads, updates, and adds. So reads are basically requests from our clients to give them the last price of a particular stock. And we get 10 million reads per second, which is a pretty high number. We also have 1 million updates per second, and an update is basically just updating the price of an existing stock. And finally, we have 1,000 add operations per day. So this is a really low frequency operation, and this is when suddenly a new stock shows up. So we have a name price pair that we have to start tracking, which we didn't know about at the beginning of the day. And we need to design a collection that handles these requirements and also supports many, many threads performing these operations at the same time. Because it's really unlikely that a single thread could satisfy this many reads and updates. Now, the basic idea of associating a name with a value is just a dictionary. I mean, nothing new here. So we could just use a dictionary with a single big lock that protects the whole dictionary. If we do that, we essentially are using just one thread. I mean, there will be one thread that's doing something, and the rest of the threads are waiting. We could use a concurrent dictionary, which is a collection designed for concurrency. It's a dictionary, it has pretty much the same operations, and it takes fewer locks, but it still takes a bunch of locks. When you read, when you write a concurrent dictionary, you are taking a lock every time. Any other alternatives? Yes?
Immutable collection, or immutable dictionary.
A what?
Immutable.
Immutable dictionary. But what about the adds? I am sometimes adding new name price
So
pairs.
as long as you read from the, well, as long as everybody tries to read from the same reference to the dictionary, as long as you update, when you update the reference to the dictionary, you add in, you add it still be slower. But you would get the adds when, as long as you updated them.
No, but I mean, suppose I have this immutable dictionary.
Yeah.
What do I do when a new stock comes up?
You replace it with a new dictionary with the extra value.
Oh yeah, but in the meantime, I have this invalid state. No?
Well,
I mean, suppose that I've added a new stock, and then immediately afterwards I received an update for that very same stock, and another update and a read. I mean, this separate copy that I have would somehow need to be updated. But it is a very good idea, I mean, to keep this state, to keep almost everything immutable, or at least immutable in terms of structure, right? So the basic idea, which we call a safe, unsafe dictionary, is the following. We have two parts to this dictionary, a safe dictionary and an unsafe dictionary. The safe one is the immutable part. It's initialized in the morning with the 100,000 stock name price pairs, and then reading from that first safe part does not require locks at all, and updating a stock, updating the price of the stock in that safe part also doesn't require locks, because I'm not changing the structure of the dictionary. I'm just updating a value that's already there. And updating a value is just writing an integer or a float to a memory location, and you can do this atomically on 32-bit or 64-bit systems. So I can just update existing name price pairs as long as I don't add anything or delete anything from the dictionary itself. And this is the safe part. And I also keep an unsafe part, to which I add new name price pairs. So the get and put operations are as follows. Get for a key is simply checking whether the safe part contains that key. If it does, I return the value without any locks. Otherwise, I need to take a lock and check the unsafe part. Put key value is simply, if this value is in the safe part, then again, I update it without any locks. Otherwise, I take a lock and update it in the unsafe part.
Does this then have the assumption that we have downtime each day and we can repopulate safe where everything got introduced to unsafe that day?
Right, so
Otherwise, unsafe, then just going to overtake safe and get
yeah,
lots every time.
yeah, well, I mean, theoretically, you could work without this downtime for a few weeks until you do get an opportunity to merge. So I totally agree that you should at some point merge the unsafe part into the safe part. But I mean, if you don't get the opportunity to do that, then under the rates that we have here, we have 100,000 name price pairs initially and only 1,000 added per day. So, you know, this unsafe part is still relatively small. Now, assuming that the distribution of requests for stocks is uniform, then 99% of the cases, we don't need any locks at all. The gets and puts, if it's in the safe part, do not require any locks, no synchronization. There is still this issue of cache invalidation, but there's hardly a way to get around it. I mean, if I update a name price pair, which is also in another CPU's cache, then yeah, I mean, that CPU is going to have to throw that out of its cache. But other than that, there's no synchronization here. And the only synchronization we incur is for the unsafe part. And even then, there are still some options for optimization, like using a concurrent dictionary, because it has more fine-grained locks, which I've mentioned. Using reader-writer locks, if I can convince you that we have more reader threads than writer threads, which actually this example says many reader threads, many writer threads, but if it's not the case, and we could use reader-writer locks and reduce synchronization even further. But again, the basic idea is just this immutability, which really helped. Okay, so this was one example of sort of creative concurrency, picking a collection that helps reduce synchronization. Another thing I'd like to mention, if not explore any more deeply, is lock-free code. This interlock class with the interlocked methods is really helpful for not using locks, for not using high-level operating system locks, like reader-writer locks, events, monitors, the lock statement in C#. In some situations, you can get away without using a lock by using one of these interlocked operations. Compare exchange specifically is a very powerful interlocked operation, which I'm not going to explore with you today. And there is also a synchronization primitive based on interlocked compare exchange, which is called a spin lock. And here, again, just in a few sentences, a spin lock is a lock, like a mutex, like a monitor, like a C# block statement. So it's a mutual exclusion primitive, which you can enter and exit. A single thread can be inside the lock at any given time. But a spin lock is not implemented by using operating system support. You don't ask Windows to put your thread in a waiting state and wake up later when it's supposed to wake up. Instead, you use a single global flag in memory that says if the lock is available or not, and you spin to enter it. So if you need the lock, just wait for the flag to become available. And to release the lock, you set the flag to be available. So you use absolutely no operating system support, and instead you just spin around in user mode, waiting for the lock to become available, and of course wasting CPU. You're sitting there and wasting valuable CPU cycles. And the only reason to use this sort of spin lock, and not the one on the slide, by the way, it says don't use the spin lock. There is a spin lock class in the TPL, which you should use instead if you consider to do this. The only reason to use a spin lock if the operation that you're protecting with a lock is really, really, really fast, like maybe a few dozen CPU instructions. If that's the case, taking a standard lock and releasing a standard lock might take more time than the work you're doing under the lock's protection. And in these situations, a spin lock, which does not use operating system support for taking a lock and leaving a lock, can be a faster option. Again, I'm not exploring this and I'm not showing you any demo, I just wanted to bring that up as an option. I'm going to leave a few minutes for questions towards the end. Another thing to think about is the TPL data flow framework, which I've already mentioned. There was a great talk earlier today, and really I encourage you to explore it. It's really suitable for situations where you have compute-intensive tasks which require a certain order. You have to do A, and then B, and then C to a certain set of inputs. And TPL data flow relies on blocks that you use to organize your concurrent processing. You pass data from one block to the other, to the third, to the fourth, and there's order implicit in your processing. This is a great framework for this sort of scenario. Another thing to consider, which isn't available today to .NET developers, is the GPU. Again, I've mentioned at the beginning of the talk that the GPU is really an untapped source of parallelism. A typical desktop-grade GPU has anywhere between 256 and 1,024 cores. This is a really powerful parallel processor that you have at your disposal, and most of the time it's idle doing nothing. And there are certain compute-intensive tasks that can be easily adapted to the GPU. And for C++, Microsoft have a framework called AMP, Accelerated Massive Parallelism, which is a set of library functions that you can use to parallelize C++ code to run on the GPU. And the compiler and library do the heavy lifting of translating your C++ code to HLSL, compiling it to native language that your graphics card understands, copying memory around. All these really unpleasant tasks are handled by AMP. Again, this is C++ only for now, but of course you could rewrite a part of your system in C++ AMP and call that from .NET. So this is an option for really intensive compute applications that need this power, which is really usually there at the user's machine and you're not tapping into it. The third thing that I've also already mentioned is SIMD, single instruction, multiple data. These are instructions that modern processors have that can operate on more than one element in a single instruction. For example, you can add 4 floating point numbers to another tuple of 4 floating point numbers in a single instruction. It takes your CPU the same time to add 4 floating point numbers as it takes the CPU, as the time it takes to add a single floating point number to another. And so, again, SIMD is only available if you have a compiler that can generate these instructions. And the C++ compilers can, the .NET compilers cannot. And Mono, by the way, which is an implementation of the .NET framework for Linux, they actually have an extension called MonoSIMD, which is basically a set of types that you can use from your C# application, and they're translated down the pipeline to the right native instructions which perform these operations on multiple elements. However, I guess most of us are using .NET on Windows and using the Microsoft .NET framework. There has been some work and some rumors about a possible direction that Microsoft might also invest in this space of SIMD parallelization, of automatic SIMD parallelization. Again, we just have to watch the news. Build is happening right now in San Francisco. Maybe we'll hear something new about that as well. So SIMD, yet again, for compute-intensive tasks, it's a great way of getting more performance out of your processor, sometimes up to 4 or 8 times the speed of standard floating point or integer operations. And slide. Before I leave a few minutes for questions, let me just wrap up by sort of summarizing what we've seen. I wanted to remind you actually, of the TPL basic APIs, which really revolve around task parallelism, where you can somehow extract the concurrent parts from your code by taking functions and pieces and recursive calls and using that as the source of concurrency. And data parallelism APIs, where you have a collection and a numberable, an iteration space, which you can use to tell the TPL how to split your works into smaller chunks and parallelize your computation. When you parallelize, a applying thresholds is a really important takeaway. If you create tasks or loop iterations that only take a few CPU instructions, you might end up doing more harm than good. And we have seen, for example, a hard threshold on the size of the array that we're sorting, which is one way of limiting the concurrency that you get. And the concurrency visualizer is a really good friend here. It can help visualize exactly what your application is doing, how many threads are working at every given time, which tasks are running, how long each task is executing, any blocking patterns in your code. We really haven't seen enough of it. It's a really, really useful tool. I can recommend a couple of books. The first is Parallel Programming with Microsoft.NET. This is a book by Stephen Tao and friends, a patterns and practices book. Not very long, and it has a body of samples and examples of using the TPL with real-life situations. Really, really good. There's a book by Joe Duffy, Concurrent Programming on Windows. This is a really long book. It covers the C++, Windows, and C# APIs. It's not very new. I think it was printed in 2008 or 2009, so it's not really up to date with the TPL, but it does give you the background on synchronization, interprocessor issues, caching, memory models, threads versus thread pools, a really good reference. And finally, there's also my own book, Product and Performance, in which I have a couple of chapters focused on parallelism as one of the ways of improving the performance of .NET applications. So here are my details. I will post the code and the slides again to my blog. I haven't made any significant updates from the memory stick that you received, but I will put everything on my blog and my Twitter account. If you'd like to ask any questions after the talk, really feel free to contact me through my blog and through Twitter. Thank you very much for coming, and we have a few minutes left for questions, so I'll be happy to take any questions. Yes, sir.
Can I take you back to the spin lock you were talking about?
Yes.
So you advocated using it for small tasks that compute really quickly. Why wouldn't you use it for larger tasks? What are you losing by using it rather than a conventional lock if you want to do a larger computation?
Oh, yeah, okay. If you use a spin lock to protect an operation like opening a file, writing something to the database, larger operations, right? You waste CPU cycles. While you're spinning for the lock, you're just sitting in a loop testing the flag. The CPU can do nothing else while you're at it. So you're completely burning a core while waiting for the spin. Of course, at some point you will get context switched to another thread, but as long as you're waiting for the lock, you're just burning CPU cycles.
You're just stuck checking it again and again.
So if you wait for something that will become available 5 seconds from now, then you have 5 seconds of wasted CPU time right there.
Yep, got it. Thanks.
What happens with a spin lock on just a single core machine?
A spin lock on a single core machine? Yeah, a spin lock on a single core machine is really bad because while you're waiting for the spin lock, obviously the other thread cannot make any progress. A good spin lock implementation will take that into account and, for example, stop spinning if it detects you're on a single core machine and the lock is taken. There's also something to say about hyperthreading, because if you have a hyperthreading system, then while you're waiting for the spin lock, there is an instruction that can say, I don't really need this core, give it to the other thread if it needs it. So there's a variety of best practices there for implementing spin locks. And that's one of the reasons you should never use this one you've seen on the slide. The spin lock from the TPL addresses hyperthreading. It has exponential backoff, so it does sleep at some point if it sees it's not getting the spin lock after a certain number of iterations. It's an art writing spin locks, and I don't pretend to know exactly how to do it.
Can you specify the limit of cores you can use as well?
Oh, what?
Can you specify the limit of cores you can use rather than taking all 8 cores on a server?
Yes, spin lock, you can limit the number.
Not a spin lock, just a parallel to
The time, you mean in terms of time?
There's a parallel options object you can pass to limit the threads.
Oh yeah, the number of cores that you're using. That's what you mean. Yeah, you can limit the number of threads that will be running concurrently, In other words, the maximum number of processors you will be using. Yeah. Yeah, so that you have with parallel for and parallel for each. You don't have that with tasks. When you create tasks and you want to limit the level of concurrency, you need to use a scheduler, your own scheduler, which will limit the number of threads.
Is that quite a big task, writing a custom scheduler? Or
I'm sorry?
is writing a custom scheduler quite a big task, or can you use it with Parasols or the
Oh no, it's not a big task. It's basically overriding a couple of functions from the task scheduler class. I mean, if your scheduler is complex, then yes, it is a complex task. But if you just want, for example, a scheduler that runs everything on a single thread, it's literally 15 lines of code, this kind of scheduler. Another example of a scheduler you might need is a scheduler that runs everything on the UI thread. And there is one provided by WPF and by Windows, but that's another example of a really super simple scheduler. There is a sample of a priority-driven scheduler with the parallel samples that I've mentioned, which accepts a priority argument for which priority your task has. Another cool idea, which is not part of the TPL. So schedulers is an interesting topic. Alrighty, so you have 5 minutes extra for your coffee break. Again, thank you very